Welcome to this video on the road to quantum reality. In this video we will show how our previous work on 1 and 2 dimensions extends naturally to the third dimension for grid structures of FRs. We will then move on in a rather hand-wavy manner to look at how the structures might lead to the Pauli Exclusion principle, which infers the fermionic nature of the electron. So let's look at extension to 3D. It's been mentioned before, but we are only considering a cubic lattice. You could say that the whole of this video series has been an adventure in experimental computation, and we have only done our experiments on linear, planar grid and now cubic grid structural forms. Without doubt, other structural forms could be investigated, and perhaps I or others will do so in due course. The choice of a 3D grid is quite significant now because another form is quite obviously available in 3 dimensions. We could consider a planar grid in which each FR is drawn out like a filament in the Z direction as an alternative to the cubic grid. I haven't done this, or if I did, it's so long ago that I've forgotten. And the cubic form opens the door to a very interesting interpretation. So that's what I'm describing here. The method is an obvious extension of the 1D or 2D eigenvalue approach. We construct a matrix which enables us to calculate the discriminated contributions of each FR from every other FR, and then we use the standard SciPy eigs module to find eigenstructures and eigenvalues. As you might imagine, size is now extremely limiting. Remember, to do similar calculations on a hydrogen atom would require going out to a radius of a few hundred Compton wavelengths. So the matrix would increase in size as the cube of this, which means that such a calculation is not feasible. Anyway, I managed to get out to a radius of about 26 or 27. And even so, it works. Let's look at some of the results and explain how they are plotted. In these figures, each blob is an FR, and the size of the blob is scaled to the magnitude of the FR squared. The colour is the phase of the FR, except that phase alternation, which is present as usual, has been removed so that the underlying phase variation can be seen more clearly. Remember, we are now tentatively associating the gradient of this phase with the velocity of the flow of wave energy within the structure. Now let's look at the first structure, and we see that it is essentially spherical. Here we look at a view along the z-axis, so looking at the xy plane, and also a view along the x-axis, so a view of the yz plane. They look the same, which is reassuring considering that the xy plane has been singled out as the plane of rotation. And we know that the Schrodinger solution, which ignores spin completely, also predicts spherical solutions. So we are maintaining isomorphism with Schrodinger for the first structure, at least when size is not too constricted. Moving on to the second structure, we see that it has the characteristic dumbbell shape when viewed in the plane of rotation. I mean, the dumbbell is along the z-axis, so that viewed along the z-axis it looks circular. This is the form associated with the Schrodinger orbital with n equals 2, l equals 1 and m equals 0. The different phases of the two lobes is very apparent. The third and fourth structures lay in the XY plane, so these views are looking along the Z-axis. They are very similar to the 2D structures which we found. They are closest in form to the chemist's picture, but the likelihood is that they could be combined to give the orbital AM bases, as was the case in 2 dimensions. I have to admit I haven't tried this. In such a combination, they would correspond to n equals 2, L equals 1, and m equals plus or minus 1. The structures continue to conform to Schrodinger solutions, so I won't go through them all. But I particularly like the sixth one. This is a dumbbell in Z embedded in a toroid in the XY plane. We can tell that there is no angular momentum present because looking at the view along Z shows that there is no phase gradient around any circumference. So this structure corresponds to n equals 3, L equals 2 and m equals 0. Here are a couple of close-ups to give a feeling for just how small the structures are. I used to describe the results as toy solutions because I thought they might be a bit off due to their very small size. But now I tend to think of them as real solutions for very deep potential wells. It's not that they are distorted away from some ideal, but that the structure would actually be like this. I suppose my change in outlook has come from recognising that structures really cannot be made too small relative to the Compton wavelength. You might expect them to be like this, and not like some pristine mathematical solution of the Schrodinger equation, because we know that this breaks down at the very high energies involved in this degree of size restriction. Okay, so that's 3D. I haven't studied the eigenvalues in any detail, but I want to move on in a slightly hand-wavy way to look at the consequence of these forms. Let's look at an idealised cubic grid with phase alternation, which remember is present in all the structures but has been suppressed in these figures. Assume that the amplitudes at each vertex are the same for the sake of this argument. What would a discriminator at capital A measure? Look at small a and small e. They are, of course, equidistant from capital A, and because they have phases differing by pi, any contribution from one would be exactly wiped out by the other. But this is the case for every pair of FRs on the cube, so the result of the discrimination at capital A must be 0. Likewise, a structure based on a grid of all points like capital A would have 0 effect on the lowercase structure. It seems that 2 and only 2 structures might occupy the same space. However, if we consider the spin of the lowercase structure and the fact that the waves forming the upper and lowercase structures necessarily overlap, then the requirement for the spins to be opposite is apparent. Superficially at least, this implies that our structures would lead to the Pauli Exclusion principle, and thus to the fermionic nature of the electron. As I said, a bit hand-wavy, but it should be possible to perform the calculations using the current method, and perhaps I will find time to do it, or maybe somebody else would like to give it a try. Thanks for watching, and I hope you have found it enjoyable and thought-provoking. I'm going to take a bit of a break from making videos for now. Real-wave quantum mechanics has a lot of loose ends to tidy up, but I think it is probably more important to put the concept out there at the moment. If any of you, hobbyists or professionals, could be persuaded to look at it more closely, I feel sure that the loose ends would be resolved much more quickly. I haven't provided the code for the calculations I have used, but I have described in detail what I've done. There are a couple of reasons for this. Firstly, my code is nowhere near professional standard, and it would take me more time than I want to spend to make it so. Secondly, I would be much happier if others could duplicate the results from scratch, so to speak. Real-wave quantum mechanics is nowhere near a complete theory at the moment. My gut feeling is that the convolution process it uses might be mathematically equivalent to Dirac's equation, but it's way beyond my mathematical abilities to prove it. I would be very interested in such a proof, or indeed in its disproof. Certainly the structures I have found have a lot in common with the Dirac spinor descriptions. One loose end that it is reasonably simple to show is that the energy of a free particle given by the Dirac equation is the same as that given by the real-wave quantum mechanics process for the energy of a free structure. I titled the video series The Road to Quantum Reality because I think it pretty much sums things up. It is, to my mind, the path quantum mechanics might easily have followed in the early days without the excessive philosophical input it was subjected to. I think it is important to note that real-wave quantum mechanics does not turn current quantum mechanics on its head. As we've shown, the results obtained are Schrodinger-like, so anything derived following the Schrodinger equation could equally have been deduced from real-wave quantum mechanics. But real-wave quantum mechanics is a hugely richer physical model than the massive charged point particle model. And as such, it seems to me to make many interpretational issues go away. As I pointed out, quantum mechanics has to call spin intrinsic because there is no space for it to be interpreted within the traditional model. Whether fully investigating real-wave quantum mechanics would lead to some testable predictions remains to be seen. One might argue that its predictions so far are all retro predictions. If I could give one final analogy, I feel a bit like an amateur metal detectorist trying out an empty field while everyone else rushes on past, taking the left turn in my introduction picture. Everywhere I look, I seem to find gold, and I'm now shouting out, "Come back and look at this." Thank you for watching these videos. Please like and subscribe, and don't forget to tell all your physicist friends. But even more important, if you are able, come and join in.